Okay, so today we're going to be talking about equilibrium. So in the last lecture, we looked only at firms. Now we'll look at the whole equilibrium in a market. And we'll start by talking about what are usually the sort of core technical topics of general equilibrium theory: existence, the correspondence principle, which relates uniqueness and comparative statics to the stability of equilibrium, and the role of income effects. But I'm going to try to give a little bit of a different spin, as you may have noticed that I like to do, on these very classic topics. I'll try to talk about how the same things that guarantee existence of equilibrium are the things that we would intuitively think need to be satisfied in order for equilibrium to make any sense in the first place, in particular that there's a large number of people in the market. I'll then talk about how to intuitively connect comparative statics, uniqueness, and notions of stability, and try to give you a sense for how that relates to basic intuitions you'll have from single-person optimization problems, which are quite a bit more intuitive than our general equilibrium problems. I'll then try to convince you that in most applications that we'll think about, income effects, which are one of the main sources of complexity in general equilibrium theory, are actually not very important. And therefore, we'll see that in some ways, general equilibrium is really just very similar to individual maximization, and therefore maybe not as complicated as it might initially appear. I'll then talk about some applications of general equilibrium theory to a range of different areas, to international trade and quantifying the benefits of improvements in transportation infrastructure, to creating artificial markets to allocate courses among students, and to two-sided matching problems where market equilibrium is reached without the use of prices by rationing based on the preferences, say, of schools for admitting students. And finally, I'll talk about the so-called welfare theorems and the role of information in determining the relative performance of markets and centralized institutions. First, I'll talk about redistribution and what the second welfare theorem tells us are the best ways to redistribute wealth. And then I'll talk about the first welfare theorem and how it's not nearly as market-friendly as you might think it is, and how information technology is increasingly making the principles of economics favor centralized institutions. You might call them socialism of some form. So, okay. Let me start by talking about sort of the core technical topics in general equilibrium theory. So, all the standard analysis of general equilibrium that you probably learned from someone like Miguel, who taught you intermediate economics or introductory graduate economics, all assumes that everyone has very smooth preferences. But if there are discontinuities in people's preferences, or their preferences aren't convex, you can have problems with equilibrium existing. Now, this might seem like a very technical problem. Aren't people's preferences smooth and so forth? But let me give you some simple examples, which I think will persuade you that in most realistic situations, in fact, there are non-convexities in people's preferences. For example, you don't buy 0.2 of a house or 0.8 of a car. Or when you're buying electromagnetic spectrum, which is a very common application of economic principles. The US government and many other governments, Colombia is just doing it now, auction off the rights to parts of the electromagnetic spectrum. But you can't buy tiny little bit of the electromagnetic spectrum. Or if you could, it wouldn't be worth very much to you, right? So in those types of situations, the standard arguments that you learned in your classes for existence of equilibrium are not true. And in fact, the whole framework that you learned in those classes will typically say that equilibrium doesn't exist. So let me try to give you a simple example of why that could be the case. So imagine that there are two people and there are two goods. So Charlie, the first person, views the two goods as perfect complements, and getting those two goods is worth $1 to him. Sonia wants to get only one good. Getting the second good isn't worth anything to her once she already has the first good. And she values getting one of the two goods at 75 cents. OK. Now, there's no equilibrium in this situation, no prices that will cause the market to clear. And is Juan Rojas here? Yeah, Juan. Could you explain why there's no equilibrium in this situation?
For it to be an equilibrium, they both must be like different in the choices. So Sonia will only value one good at most 0.75, while Charlie will need to buy both at one. So that creates a sort of like contradiction between both of them. They cannot trade. So at a certain point they won't be able to find equilibrium prices.
So why don't you go through some potential equilibrium prices and show what would happen at each of those?
If it's 0.75, Sonia will be able to buy one of the goods, and Charlie wouldn't get any.
So if they both cost 75 cents, you're saying? Yeah, so then Sonia would buy one, Charlie wouldn't buy any, so you would be left with one good that would be unheld by anyone, right? What if the prices were lower than that?
If the prices were lower than that, then Sonia would still buy a new one.
Yep.
And they would need to each cost less than 0.5 to Charlie to buy both.
Yeah. But at that point, you would have excess demand, right? Because Charlie would be buying both and Sonia would be buying one, right? So at any prices where Charlie is willing to buy both, Sonia is willing to buy at least one of the two of them, right? And so that'll create excess demand. If the prices are higher so that Sonia doesn't want to buy one, then Charlie won't buy them. So there's no way to make an equilibrium in this market, right? OK. Now, let's think about what the efficient allocation is, right? The most utility we can get by giving anything to Sonia is 75 cents. The most utility we could get by giving things to Charlie is $1. We can't give it to both of them, because if we give both to Charlie, then we can't give one to Sonia. So the efficient allocation is to give both to Charlie, and yet that's not an equilibrium in this market, right? There is no equilibrium in this market for the reasons we just went through. So what gives, right? This seems like a pretty reasonable type of a situation, and yet we can't find an equilibrium, right? The thing to notice is that there's only two people in this market. And that's very important, right? So when we think about general equilibrium, we think of people as taking prices as given. But if there's only two people, that's a bit of a crazy assumption to make, right? What would actually happen in this type of a situation? Imagine Charlie started with both of the goods, and he knew that one was worth 75 cents to Sonia. Well, he'd know that it wasn't worth selling one to Sonia, because even if the prices were, say, 75 cents each, she wasn't going to buy actually both of them. So he wouldn't take those prices as given. On the other hand, if Sonia started with both of the goods, she wouldn't just naively try to sell one to Charlie, but she knew he wouldn't take that unless she also offered him the other one. And so she would take both of the goods and she would sell them both to him for $1. So the idea of equilibrium here is a bit silly, because people don't have any reason to act as price takers, right? Because there's such a small number of people. So the non-existence of equilibrium comes from the fact that equilibrium is not really the right way to think about what's going on in these markets, right? So in what sort of a market would there be would it make sense to think of an equilibrium? Well, let's imagine that rather than just being, one Charlie and one Sonia, there's a bunch of people named Charlie and a bunch of people named Sonia, right? And everyone who's named Charlie values the goods as Charlie does, and everyone named Sonia values the goods as Sonia does, right? Then the question is, and imagine, so to model that, let's say there's a mass 0.5 of identical people like Charlie and a mass 0.5 of identical people like Sonia, and there's a mass 0.5 of each of the goods, right? That's the continuum replication of the original economy we had. We just took the economy and we kept multiplying it until there was an infinite number of people, right? So that no one could have an impact on a price, right? Okay, now Oscar Solis? No, Oscar. Does anyone else see what the equilibrium is here? Yeah, go ahead.
Half Charlies would buy both goods at 0.5 each.
Yeah.
That would be one. And half Sonias would buy the goods at 0.75 cents.
Yeah.
That basically would be
Well, that's not an equilibrium because people are paying different prices, right? Equilibrium is something where everyone pays the same prices.
then, well, actually half Charlies would buy both prices, both goods at the
Yeah.
same price, while half Sonias would buy them at the same price.
And what price would that be?
0.5.
Yeah, it needs to be 0.5 because that's what leaves Charlie indifferent between buying the bundle or not buying the bundle. So he's happy to do either. And the price of the two goods have to be the same because that's what makes Sonia indifferent between buying each of the two goods, right? So we satisfy half of the Sonias with each good, and we satisfy half of the Charlies and leave half of them unsatisfied. The prices are 0.5. And this is optimal because if you think about it sort of on average, Charlie gets 0.5 units of utility from each good, whereas Sonia gets on average 0.75. So you want to satisfy all the Sonias first and then deal with the Charlies, right? Okay. So prices are 0.5 for each of the two goods because this makes everyone indifferent. Now let's think about what would have happened at the prices 0.5, 0.5 in the finite two-person economy. Is Alberto Reyes here? Alberto? No? So what would have happened in the finite economy at 0.5, 0.5? Well, notice that everyone's indifferent. So aggregate demand has a bunch of different potential values, right? It could be that, Sonia demands good 1, Charlie demands nothing, in which case the demand is 1, 0. Or Sonia demands good 2, and Charlie demands good 0. And Charlie demands nothing, so then it would be 0, 1. Or it could be Sonia demands good 1, and Charlie demands both, in which case it's 2, 1. Or Charlie demands both, and Sonia demands good 1. So what does that look like? If we were to graph aggregate demand, in a 2 by 2 space, the points of aggregate demand would be 2, 1, 1, 2, 0, 1, and 1, 0, right? So they would be here, and the aggregate supply would be here. So you'd see the aggregate demand is sort of surrounding the aggregate supply, but is not actually touching it, right? If we could take a convex combination of two of the points on the aggregate demand, we would get the aggregate supply and we would have an equilibrium, right? But the problem is that the aggregate demand is not convex. Things that are in between different points in the aggregate demand are not actually in the aggregate demand. Now, when you have a large population, that's not a problem because the thing is that if there's someone here and someone here, then you can always have someone who's in between the two. You can always have some of them do one thing, some of them do the other, and that will cause it to be there. So whenever you have a large population, these problems never arise. These problems only arise because in a finite population, you have these points and you can't get something in between. Anytime you have a large number of people, there will always be a way to make them have something in between. And in fact, this will always work even in a large finite economy. So imagine that we had, rather than an infinite replication, we just had a doubling or a quadrupling or something like that. Well, then we could always do the half and half thing that we described, and you would have an equilibrium. Now imagine that you have a tripling, or multiplying by 10 or 11 or 21, something that's odd. Well, still you would have one person left who couldn't be matched up. But all the other goods could be matched up. So the amount by which the market fails to clear is only as big as the number of people that are sort of left over in that process, right? And so in particular, the market will only fail to clear by an amount that's proportional to the number of goods rather than the number of people. So anytime there's a large number of people, markets will almost always almost perfectly clear, right? Okay. So one thing that you could say is that the allocation 0.5 is in some sense an approximate equilibrium, in the sense that if there were a lot of people, the market would almost clear. And here in this situation, even though it's the case that we don't have a point where the aggregate demand exactly equals the aggregate supply, it's also the case that if, what's the motivation behind equilibrium? If there's excess supply, you think that prices should go down. If there's excess demand, you think prices should go up. This is a case where there's neither excess supply nor excess demand. There's both at the same time, right? So in some sense, there's no systematic pressure being put on prices to move any direction. And so you can think of this as being sort of approximately an equilibrium in some sense, except that it doesn't even really make sense to think about equilibrium in this context, because every individual person can have huge impacts on the prices because there's only two people. So in any case, this is a simple example, but I think it teaches some much broader lessons, which is that when you have a large number of people or you have uncertainty, this tends to convexify the demand and always leads to an equilibrium to exist. And this is true in game theory as well as in general equilibrium. So most cases when equilibrium fails to exist in game theory are cases when you've either put in too few people or you've put in too little uncertainty about what people's values are. If you just put in a little bit more uncertainty, you almost always restore the existence of an equilibrium. And because it doesn't make any sense to think of people as taking prices when there's a small number of people, you should really conceptualize those circumstances as oligopoly or monopoly. Anytime you think it's reasonable to apply general equilibrium, you should think about there being a continuum of people. And whenever there's a continuum of people, equilibrium always exists. So equilibrium is always going to exist in all the cases where general equilibrium is the right way to think about the economy. And even more broadly than that, the basic lesson is if you write down a model and there's no equilibrium, don't take that as an indication that things are really inefficient or things are going to be crazy or whatever. Instead, take it as an indication that you've written down the wrong model of the situation you're thinking about. Non-existence of equilibrium means that you're sort of thinking about things in some fundamentally inconsistent way. Yeah?
Does it make any sense to think continuum people and agents?
Well, I mean, in the same way that it makes sense to think about using the central limit theorem to approximate smaller numbers in statistics. That basically the behavior of a finite economy with a large number of people is going to be very similar to the behavior of a continuum economy. So, but it's much easier to analyze a continuum economy than it is a large finite economy because there's all these numbers floating around in a large finite economy, whereas things are very smooth and easy to analyze in a continuum economy. So the right model to think about large markets where there's a lot of anonymous people is in terms of a continuum economy, I think. And in the worst case, you should change the notion of equilibrium. So this notion of approximate equilibrium is sort of something that's close to actually an equilibrium existing, which makes sense to think about in a finite economy. So the main point here is that don't be a slave to definitions and formalism. Just because the definition of equilibrium is X and we were formally considering an economy with exactly 107 people, that might be a really, really complicated thing to analyze and might act in practice exactly how the continuum model acts or how this alternative notion of equilibrium acts. So re-examine your models when you get into things that are extremely complicated. Don't just assume that you have to follow the mathematics wherever it leads you. Okay. So now I want to talk about comparative statics. What do we usually think the effect on prices of supply rising is? Gabriel? What do we usually think the effect on prices of supply rising is? Yeah, the price should go down, right? So you'd expect quantity to rise and the price to fall. And this comes from the standard supply and demand analysis. So this is still true when we think about equilibrium in a more rigorous way, but it's slightly more subtle. And all the subtleties of it can lead, I think, to a lot of confusion about what general equilibrium says and doesn't say. And so I'm going to try to spend the next half an hour, roughly, going through the right way to think about the subtleties of these comparative statics. Let's think about a single market economy first. So it's defined by this simple equation, supply equals demand, right? So S of P, supply, which depends on price, is equal to demand plus something that shifts the supply up and down. And what we want to know is what is the impact of an increase in the supply, S, on the price. And Sergio, can you do that calculation from this equation? What is the effect of an increase in supply on the price? You can do it on your paper, or you can do it on the board, or whatever you want to do.
We have to take the implicit derivative, but
yeah, exactly.
I couldn't do it by mind. I think it just should be like d of p minus sp, but I mean 1 over that actually, because
it should be what? Say that again.
It should be 1 over dp minus sp.
SP.
S plus big S. Demand minus plus 1 over demand minus plus.
The derivatives of them, you mean, right?
Yeah.
Yeah, so let me just derive that, right? So we're going to take the implicit derivative with respect to S. So we get 1 plus S prime times dp ds is equal to d prime times dp ds, right? And so if we rearrange that, we get dp ds is equal to 1 over d prime minus s prime, right? So that's exactly what Sergio said. And this is the classic, elasticity formula. We could reformulate this in terms of elasticities. And why does this have to be negative, this number here? The claim that Gabriel made is that an increase in supply should reduce the price, right? So why is this negative? Typically, we would say, well, demand slopes down, supply slopes up. So this is a negative number minus a positive number, which gives you a negative number. But more importantly, the key is not this. That is not the key principle. That's the standard thing we assume, but that's not really what's necessary to make this the case. Instead, imagine that I were to graph in the reverse way that we usually do. I'm going to put price on this axis and quantity on this axis. Now, we usually would say demand slopes down, price slopes up. Supply slopes up. S of P, D of P, right? But imagine now that I allow the supply to actually slope downward, that actually you would have a decrease in supply as the price increases. Would that change this effect? Well, not necessarily. If supply slopes downward, but it still cuts the demand from below to above, then if I increase the supply function, it's still the case that the price is going to fall. Right? So the key point is not that both are going in the direction you expect, but the demand slopes downward relative to supply. That supply cuts demand from below rather than from above. On the other hand, if I were to switch this so that supply were actually sloping downward more quickly, right? Then if I increase supply, the price is actually going to rise rather than falling. So it's all about which direction supply and demand cut each other from. Does that make sense? Now, why am I insisting that supply and demand should cut each other in this particular direction? Well, let's try to think about what would happen if that weren't the case. So, first of all, let's start, again, with demand like this and supply like this. So supply is cutting from the right direction. And imagine we start at this point, which is supposed to be an equilibrium point. And imagine now that for some reason prices rise by a little bit. So now, at this higher price, the demand quantity, so at a lower price, the demand quantity is going to be greater than the supply quantity is going to be, right? And so what's that going to do? That's going to push prices upward, right? So they'll get pushed this way, and they'll get pushed this way, and we'll go back to the equilibrium. And vice versa if we were to start from this side, right? What happens if things are going in the opposite direction? So now let's imagine we've got that supply function, which is really, really steep. We start at the equilibrium, now we go to a lower price. Now, the supply is actually greater than the demand at this lower price. So that's going to push down prices. So prices will fall. But then that'll push prices down more, and so forth. And we'll go off in either direction. And that's true in both places where we start. So we say that that point is not a stable equilibrium, it's an unstable equilibrium, right? So in particular, let's call demand minus supply the excess demand, E of P. And what I'm saying is that the excess demand has to be downward sloping in price, otherwise the equilibrium is unstable. And an unstable equilibrium is really not any equilibrium at all. It's really, in fact, the opposite of an equilibrium. Rather than being a point that things push towards, it's a point that things push away from. It's sort of like the least equilibrium point that exists anywhere, right? So it's not something that you should think of as being like an equilibrium, but not quite a full equilibrium. It's in fact should be viewed as the exact opposite of an equilibrium. It's like the place that the market is least happy to be, rather than most happy to be. Okay, so let me try to relate that to your understanding of an individual maximization problem. So let's consider just the simplest individual maximization problem where you're maximizing f of x minus t of x, right? So we know that if t increases, individuals will have to decrease the level of x if they're optimizing, right? That's just basic revealed preference, right? Because I would always, if I had been happy to have a higher level of x when t was lower, I'm certainly happy to have that higher level of x, lower level of x when t is higher. So it can't possibly be the case that when t rises, I want to increase my level of x. Does that make sense? Yeah. So basic revealed preference tells us that when t increases, my optimal level of x can't increase. And the reason is that, let's say that the maximum is x star when t is equal to some value. Now imagine that I increase it to t prime greater than t. right? If now my value of x is higher, right, then that's saying that, let's call my new value of x, x star star. This is saying that it's better to do x star star, which is greater than x star, when we have t prime, which is higher than t, right? So that's saying that this is greater than f of x star minus t prime x star, right? But if that's true, then it's also going to be true that x star star, that f of x star star minus t times x star star is greater than f of x star star minus t x star, because if we increase t prime, that clearly just makes this side, this negative part, more negative, right? And so I don't ever want to increase the value of the thing when the cost of doing it gets greater, right? This is just basically the law of demand. If the cost of something gets higher, it's never in my incentive to do more of that thing, right? Okay. So we know by revealed preference that whenever t rises, x has to fall, right? That's just sort of revealed preference or basic common sense. It's the law of demand, right? So how do we now, using the, sorry, hold on 1 second. How do we use the same notion of comparative statics to figure out whether that's actually the case here? Well, we know that the optimal choice here is given by f prime is equal to t, right? So if we again take the comparative static, we get that dx star dt is equal to 1 over f double prime of x. Right? Because if we take the derivative of this side, we get f double prime times dx dt, and we get 1 on this side. Right? So that says that doing this mindless comparative statics exercise, rather than thinking through the underlying economics of the situation, will give us the right answer if and only if f double prime is less than 0. Which is to say, if and only if we're looking at a point that's maximizing utility. If, on the other hand, f double prime was greater than 0, that would be a minimum. And obviously, the minimum is going to behave in exactly the opposite way that a maximum will. Yeah?
Didn't we need that in the fact that f double x is greater than f x star? If x star, I mean, we comparing that given that t is high,
Yeah.
then we should have a little x.
If x is the optimal value. Here we didn't use anything about derivatives. We just used the fact that x double star was claimed to be the optimal value. That is, it's better than any other value at maximizing this function.
But we wanted to show that x double star needs to be this.
Yeah.
So in order to do that, we have a greater t. So we have to have a relation between f in x double star and in x star. And of course, if f is complex, then I think we have to.
Well, this didn't rely on convexity or concavity in any way, right? It just, look, none of my arguments had anything to do with that here. It was just saying that if this is greater than this, then this, I mean, we can difference out the f. F has nothing to do with this, in other words. You can just take f out of both of these expressions, right? You can just subtract the top from the bottom, right? So the shape of f didn't have anything to do with the logic here. But what I'm saying is that the standard analysis that we do using derivatives depends on us looking at an actual maximum. If we're looking at the minimum, the mechanical math is going to tell us exactly the opposite thing happens. Because at a minimum, we're not maximizing. We're doing exactly the opposite. And so, of course, if you increase the cost to me of doing something, then if I'm trying to choose the point that's the worst for me, I'm going to do more of that thing when you increase the cost to me, right? Because I'm trying to do exactly the opposite of maximizing utility. I'm trying to minimize utility, right? And so if we're looking at a minimum rather than at a maximum, all the comparative statics are going to reverse, right? And what I want to claim is that stability in the world of equilibrium is exactly the same as maximization in the world of an individual problem. It's exactly the same as the thing being locally concave and therefore being a local maximum rather than being a local minimum. And it plays exactly the same role in the comparative statics analysis, right? F double prime is just like E prime. It goes on the bottom of this thing, and it represents whether the thing is stable or unstable, a maximum or minimum, whether comparative statics go in the right direction or the wrong direction. Okay, so that's saying that local maximization or local stability, which I'm claiming are really just the same thing in two different problems, are equivalent to locally the comparative statics going in the right direction. Now, what about global second-order conditions from an individual maximization problem? What are the global second-order conditions, Nancy? In order for something to actually be the global maximum, what has to be the case? Not just at this one point, right? But so far we were just talking about something being a local maximum. But if I want something to be a global maximum, it's not just true that the second derivative has to be negative there. What has to be the case? Yeah, it has to be negative everywhere, right? In order for something to be a global maximum, the function has to be concave all over the place, not just at that one point, right? And in particular, that's not exactly true, right? Let me give you an example where that's not exactly true. So if I have a function that's like this, this point is a maximum even though it's convex down here. But what is true is that if I want any time that there's a solution to the first order condition for any value of t, this thing that moves the problem around, if you want any solution like that to be a global maximum, then the second derivative has to be negative everywhere. Why is that? Imagine that I can change t however I want it to. I can get this to be equal to the value of the derivative of f at any point that I want, right? Because the derivative of f is just some set of values. If I move t around, I can set it equal to the value of the derivative at that point, right? Once I get there, if f double prime is not globally negative, then could be positive at that particular point, right? And that would mean that that's a local minimum rather than being a local maximum, and therefore it's clearly not a global maximum, right? So what that says is that if we want to have what I want to call a first-order solution for any value of t, a first-order solution means that anytime you solve the first-order conditions, that's actually the global maximum. If we want that to be true for every value of t, then we have to have that the function is globally concave. So the function being globally concave is equivalent to, for any value of t, the solution being the actual optimum. Okay. This is also equivalent to the notion that if I maybe don't allow you to choose all values of x, maybe I constrain you to, say below some level or above some level, that you'll always want to choose the point that's closest to the global maximum. Okay. So both of these principles extend to stability in equilibrium. That is, we have this equivalence between local stability and local comparative statics, and between global stability and global existence of a unique solution. That is, that any intersection between supply and demand, for any way that you shift around the supply function, will represent the unique stable equilibrium. The unique stable equilibrium is the same thing as the global maximum in the context of the individual maximization problem. So these are called the local and the global correspondence principles. That there's a correspondence between local stability or local concavity and local comparative statics, and that there's a correspondence between global stability and global comparative statics. That's right, and global uniqueness. Existence of a first order solution, that any time you get the equilibrium conditions or the first order conditions to be satisfied, that will represent the unique stable equilibrium or the global maximum. So these things are exactly the same as one another. Okay, so now I've only been talking about a single market or a single thing that someone's maximizing. But in general equilibrium, we usually think about many, many markets, right? And so the relevant analogy is not to an individual maximizing one thing, but maximizing many things, right? So let me go to that analogy now. So let's think about an individual choosing a vector x to maximize f of that vector minus the dot product between some vector t and x. So this is the cost of each one of the things, right? Okay, so the optimum here is given by the gradient of f, or its Jacobian, being equal to the values of t. That's just the multidimensional version of what we did before. Now, how do we apply the implicit function theorem here, Juan? Juan Rojas. Yeah, exactly. So what would that give us here? What would dx star dt be here? Exactly. So it should be perfectly analogous to what we had here, but in the multidimensional case. So what do you think it's going to be?
The Hessian matrix is negative, but since a matrix cannot be negative in the strict sense, then it needs to be definitely negative.
Yeah, well, but in particular, what's just the expression for dx star dt? What's the equivalent of 1 over for matrices? Inverse, right? So we take the implicit function there and we get that the Hessian of f times dx star dt is equal to the identity matrix. And so we get that dx star dt is equal to the inverse of the Hessian, right? Okay, now, Juan, again, continue with what you were saying. What does it mean for things to move in the right direction here? So before we said, that when the, tax increases, you should do less of the activity, right? That's what we said before. Now, what does it mean for things to be moving in the right direction?
It should be the same but for all markets. So
yeah, right. So it means that it's negative definite, like you were saying. That is, if we take some vector of changes to the tax, then we say, and we hit the market with all of those, then if we take the set of all changes in x that occur by that, and we multiply those again by the way in which we change the taxes, that whole thing should be negative. That is, if we move the taxes in some direction, and then we ask how do the quantities move, they should move in the opposite direction in total, right? This is basically the law of demand. And it's in fact the law of demand for any set of markets held fixed. So what do I mean by that? Imagine that rather than allowing you to adjust all your x's, we held fixed some of your x's. And then we said, imagine we increase the tax on one of the things. We want you to do less of that thing, right? Regardless of how many of your choices we hold fixed. That's equivalent to saying that if we changed a bunch of things, then overall you move your actions in the opposite direction. So those are two different ways of saying a stronger version of the law of demand. That no matter how many of your things we hold fixed, if we change the tax on one of them, you should be doing less of that thing that we put the tax on. That's the strong version of the law of demand. And what this says is that there's an equivalence between this matrix being negative definite, which is the same as you being maximizing locally, right? We know from basic linear algebra or basic multivariate calculus that when the Hessian is negative, that's exactly the case when you're maximizing locally, right? And that is equivalent to the fact that if we change things by some, if we change some vector of taxes, that you'll change your behavior in the opposite direction. The reason we know that is that the inverse of this matrix is negative definite if and only if the matrix itself is negative definite. That's a classic linear algebra result. And therefore, the comparative statics will be negative definite if and only if you're maximizing at that point, right? And so there's an equivalence, again, here between this intuitive comparative static we have, the law of demand locally, and that you're maximizing locally. Now, you can also show that the global thing happens, right? Because if this thing is not negative definite globally, then we can adjust the t's to find some value where they satisfy the first order condition, but where the function is not negative definite at that point. So there's also an equivalence between having a single global maximum for any setting of the t's and having a globally negative definite Hessian of f. Now, the Hessian has to be symmetric. Why is that? Well, it's the matrix of second derivatives of some function, right? And we know that it doesn't matter which way you take the derivatives, they're always the same, right? If you take the derivative of 1 with respect, the function with respect to a, x1 and then x2, or if you take it with respect to x2 and then x1, those are the same things. And so that means that the Hessian matrix of the second partial derivatives has to be symmetric. That's also called Slutsky symmetry, right? That if you take a demand function, that the derivatives of it, of the demand for one product with respect to the price of another product is the same as the derivative of the first product with respect to the other product, right? And because H is symmetric, it being negative definite is equivalent to a bunch of other properties. Sergio, could you say what some of those other properties that negative definiteness is equivalent to? Yeah, so that its eigenvalues will all be negative, and they'll actually all be real numbers. Can you think of anything else that it's equivalent to?
Yeah, the one I was thinking, I was wondering what I read.
Yeah.
The determinant of the minus, the leading minus.
Yes. Yes. So all the principal minor. So what is a principal minor? A principal minor is you take a matrix and you choose any set of rows and columns that you want. Sorry, any set of rows that you want. And you take out all those rows and you take out all the columns that correspond to that, and you get another matrix. And you take the determinant of that matrix. That's called a principal minor. What is a leading principal minor? It's if you do that not for any rows and columns, but only for ones that are starting out the matrix. So you could take the first row and column, or you could take the first and second row and column, or you can take the first, second, and third row and column, but you only do it starting from the top. Now it turns out that with a symmetric matrix, all of the leading principal minors being negative is the same as all of the principal minors being negative. So those two things are equivalent to one another. And those are equivalent to all of the eigenvalues being negative and real for a symmetric matrix. So these are three different things. All of the principal minors being negative, all the leading principal minors being negative, and the eigenvalues being negative and real, which are equivalent when you have a symmetric matrix. Now the problem is that when we have income effects, the matrix of demand derivatives does not have to be symmetric. And when you add that up over a market as a whole, income effects can do all sorts of crazy stuff. That's very similar to the fact that we know that you can have Giffen goods if there are income effects. That the demand function doesn't always slope downward. It can slope upward. Right? So we know all sorts of funky things can happen when there's income effects. That's why in the equilibrium setting, I wasn't insisting that the supply function had to slope upward. It could slope downward. The demand function could slope upward. But remember that despite that, we still had this principle of stability that was forcing things to work well, was forcing things to go in the right direction, even though we couldn't ensure that the demand function sloped downward and the supply function sloped upward. So the question is, what is the right notion of this negative definiteness when you have a market which doesn't have to have these symmetric derivatives? OK, so let me first talk about the problem of income effects. So essentially, all the problems that show up in general equilibrium theory show up because of problems with these income effects. And symmetry doesn't hold for Marshallian demand. And in fact, the demand function doesn't even need to slope downward, as we know from Giffen goods, right? And when you add this up across individuals, all sorts of crazy things can happen. In fact, there's a very famous theorem called the Sonnenschein-de Breux-Montel theorem, which says that when you take different individuals, you let them have all these income effects that you want, anything can happen. The excess demand functions of the market can be an arbitrary function. There's absolutely nothing you can say about it. And the question now is whether this destroys the logic of the correspondence principle. Is Sebastián Cajamarca here? Yeah, Sebastián. How could we, I actually just went over this, how could we resurrect the logic of the correspondence principle here, even though things are going crazy? What sort of strategy might we try to take? What did we do in the one-dimensional case? There I had the supply function going in the wrong direction, and yet I could still make something work. So what was it that we tried to do?
In the case of Charlian?
No, in the case where I had the, I had the supply function that sloped upward, but it still crossed the demand function in the right direction, right? So what could we try to do here that's sort of similar to that? And does anyone else have a thought? Yeah, you try to think about the principle of stability rather than just the principle of everything going in the right direction. You know what I mean? You try to think, what is the right notion of things crossing each other the right way that would make this market stable, right? And that's what we're going to try to do. OK, so we're going to look for an analogy for stability when we have many markets. If a single market, you know, is just about crossing, there should be some analog of crossing in the right direction in multiple dimensions. Right? Okay. Now, when we had symmetry, all the different notions that sort of intuitively meant going in the right direction, the eigenvalues being negative, the principal minors being negative, all this sort of stuff, all that was the same. Now we're not going to have symmetry of the matrix because we have all these income effects. So what is the right equivalent definition? Well, let's let E of P be the matrix, the vector of excess demands depending on the vector of prices. Then the gradient of E does not need to be symmetric because of the reasons I was talking about before, right? The second partial derivatives of the demand functions of individuals don't have to be symmetric. And so certainly for the market as a whole, it doesn't need to be symmetric. And when it's not symmetric, this gradient of E, which was, you know, the equivalent of our derivative of the excess demand before, does not, all these different notions are going to be completely different from one another. So in fact, even if all the entries are real, the eigenvalues don't even need to be real numbers. And the principal minors being negative is not the same as the leading principal minors being negative. So all these things are different. Nonetheless, and I won't go through all the mathematics of this, mathematicians have figured out what the right concepts are here. So in particular, here's a notion of stability. Let me see. Explained better in a moment. OK, let me try to explain how this works. OK, so imagine that we move away a little bit from the equilibrium prices. Right? We want to have a notion of if we start adjusting the prices in the market, are they going to come back to the original thing? If we start adjusting them in the opposite direction of the excess demand. So if the excess demand is positive, we want to reduce the price. If the excess demand is negative, we want to increase the price. Sorry, excess demand is positive, we want to increase the price. Excess demand is negative, we want to decrease the price. Right? Now, it turns out that that is very, and I go through this in the note that's associated with the course. I won't go through it in detail here. That's exactly equivalent to the eigenvalues being, having negative real parts. But the problem is that it all depends on the relative speed at which I adjust different markets. So you have to ask, and that seems like a silly thing for it to depend on, right? We wouldn't want to say that an outcome is stable if when I adjust this market quickly and this market slowly, it goes crazy. But if I adjust this market you know, slowly and this market quickly, then it converges, right? So destability is a notion of when is a market stable regardless of the set of rates at which you allow it to adjust. And that technically is that for all strictly positive diagonal matrices, that's a matrix that has numbers that are positive and real in all of its diagonal entries and nothing off the diagonal, and corresponds intuitively to changing the rate at which the markets adjust, that that matrix multiplied by the gradient of E has to have strictly negative real parts. That's what means that a matrix is destable. It means that no matter how relatively quickly I allow the different markets to adjust, I always come back to the equilibrium point after I move away a little bit. OK. A second notion is what's called Hicksian. That says that all the principal minors, not just the leading principal minors, but all the principal minors are positive. And that I won't go through the intuition, but is actually quite similar to this notion of things crossing in the right direction. Because you can, well, I won't go through it. But anyways, you can talk to me later if you're interested about why that's similar to things crossing in the right direction. Now, it turns out that destability implies that something is Hicksian, and that Hicksian is equivalent to the strong law of demand that we were talking about before. That if I hold any set of markets fixed, and I increase the tax, that the amount of stuff going on in that market will go down, that the prices in that market will change in the right direction. So this gives us a version of the local and global correspondence principles. So being a Hicksian matrix is equivalent to strong comparative statics and is implied by the stability of the market. And globally being Hicksian turns out to be equivalent to any market equilibrium being a globally stable equilibrium, which is again implied by the things being globally destable. So all this is a lot of quite complicated mathematics and perhaps a bit hard to follow and sort of thing that you should go back and look at the handout on. But the key point is that anytime you think of some complicated general equilibrium problem, you can always go back to your basic intuitions from the one-dimensional individual maximization problem and say, look, if I'm getting some weird outcome here, it must be because I'm looking at the wrong type of thing. I'm looking actually at something that's more like a minimum than like a maximum. And if I want to get uniqueness, well, I'm going to have to figure out what's the relevant equivalent to global concavity of the function. So even though these things are much more complicated, really the only thing that's more complicated about them is the mathematical terms you have to memorize to go along with them. But the basic concept is the same as in a simple individual maximization problem. OK. So these principles are useful not only for general equilibrium theory, but also for game theory. Because in game theory, you often have equilibrium defined in terms of some set of first order conditions, some equilibrium conditions being equal to something. And when you do comparative statics in the game, it's exactly like doing comparative statics on a market equilibrium. And again, you can get non-symmetry because different people in the market aren't necessarily maximizing the same objective function. But the subtleties here, which created the difference between the individual maximization problem and general equilibrium, were these income effects. Those income effects, I want to try to argue now, are not actually that important in practice in most general equilibrium settings we're going to talk about. And how intuitively can you think about this? Well, notice that we know Giffen goods exist in principle. But in practice, it seems very, very rare that you would actually have a Giffen good. And also in practice, income effects more broadly are going to be very small. And therefore, in practice, usually things are Slutsky symmetric and therefore stable. And all the much simpler math that just goes along with the individual maximization problem applies to the market equilibrium. Why is that? Well, first of all, I'm going to talk about quantitatively how big of a part of your income things would have to be in order for income effects to matter, and what is the relevant notion of income. OK. So Bobby Willig, in a paper you guys were supposed to read, calculated how large income effects have to be before they actually matter for the things we care about. Now, what are the things we care about? One thing is these issues of stability and comparative statics and so forth. But another one that's very simple and that you guys probably learned quite a bit about was computing consumer surplus. When you have large income effects, consumer surplus gets very complicated. There's this Hicksian compensated versus uncompensated, and there's the compensating variation versus the equivalent variation, and all these things are messy. We can't just do the normal thing, which is take the area underneath the demand curve. Right? And Bobby Willig tried to say, how bad of an approximation is the area underneath the demand curve? Here's how the calculation that he did. So let's call A the standard consumer surplus that you would calculate by just looking at the area underneath the demand curve. And let's let I be the total income you'll earn over your lifetime. And let's let eta, absolute value of eta, be the largest value that the income elasticity takes on over the range that's relevant. So we know that income elasticities are usually about 1. Most goods are pretty close to normal. Sometimes it's a bit less. Sometimes it's a bit more, but it's almost never, you know, greater than, say, 3, right? So what Willig shows is that the percent error that you make by just computing the normal consumer surplus, rather than these more complicated things of equivalent variation or compensating variation, is less than the absolute value of the elasticity times the fraction of your lifetime income that the change in consumer surplus accounts for, divided by 2. So let's take an example of that. Imagine that we never get income elasticities above 3, and that the things we're thinking about are no more than 1% of your lifetime income, which is a massive amount of money. I mean, 1% of your lifetime income, you know, most of you probably have lifetime income around $1 million. It would have to be like a $10,000 effect on an individual for this to matter, which for most of the things that we're talking about is like, you know, that's a massive effect, right? Then the error that you make by using consumer surplus rather than these complicated things is about 1.5%. Now, if you did a statistical analysis and you got an error of no more than 1.5% of your answer, you would have a paper in the QJE, right? As long as it was an important topic. I mean, that's an incredibly tiny error. You almost never see errors that small for things. Usually it's like 50%, right? So the amount that it matters to include these income effects for this consumer surplus calculation is basically 0 for anything that's not just some massive part of your lifetime income, right? This is very similar to Rabin's theorem that we talked about on Monday, right? It says that even though there are these income effects broadly, over almost anything that in real life we really think about, these things are so small that you can basically forget about them and just treat it as if everyone had no income effects, right? So to make clear how massive things would have to be in order for it to matter, Bob Lucas calculated that the total cost, and this is almost certainly wrong and way exaggerated, but it still gives you a sense. He calculated the total cost of all business cycles for the history of the world was about 0.0047 of people's lifetime income. And that would say that the error of just using consumer surplus measures to measure the cost of all business cycles, do you think business cycle, really macro thing, where clearly income effects should matter, would be 0.008. So another example is Eden and Cordham, who we'll talk about below, calculate that the value of all international trade is about 15% of the income of the world. And so what that says is the percent error that you make if you even considered a model where you eliminated all international trade. I mean, we never would think about that. We think about little changes in tariffs. But if you eliminate all international trade, force countries back to autarky, and you just use consumer surplus to calculate that, you would only make about a 25% error, which is almost certainly tiny compared to almost everything else that went into the assumptions of modeling, the statistics, all that sort of stuff, right? So income effects, even though in principle they exist, almost never matter when you're doing a microeconomic analysis. So for almost any standard microanalysis, this stuff is just totally irrelevant. And one huge reason is because of Friedman's permanent income hypothesis. The income that we're dividing by is not the income that you earn this year. It's the income over the whole course of your lifetime, which is a very large number. You know, for a standard professor, maybe it's $5 million, right? So imagine you value a particular election at $1,000. You're willing to pay $1,000 to see your favorite candidate win versus your least favorite. Well, then the error that you would make by assuming that people have quasi-linear preferences over that they have no income effects, is 0.0003. How about if the price of your car were to double and become $20,000, right, higher? Imagine you're buying a $20,000 car. The price of your car doubles. The error you would make by doing that for any reasonable income elasticity would be 0.006, right? Eliminating all fees on investments that you pay during the rest of your life, which is much bigger than most of the things we consider in finance, that gives you an error of 0.009 if you use things. And when we start getting up to something massive like an estate tax, which maybe will cost you $500,000, even there the error is still 0.15, which is significant but not very large. Okay, So what that means is unless we're talking about some massive economy-wide thing that affects everyone in some huge way, assuming people have quasi-linear utility, which is what we'll do during most of the rest of the course, makes perfect sense. And through most of the course, we're going to be talking about stuff that's like about individual industries. So this assumption is almost perfect in those contexts. So for the remainder of the course, we'll use this assumption that people's utility depends on some goods that they get plus their wealth. That they have quasi-linear utility in wealth, which is equivalent to there being no income effects. Okay. However, is Camilo Ramirez here? Camilo? No. What do you people think are some examples of things where where income effects might actually matter? Topics we might talk about potentially in a course like this. Anyone give me examples? Well, one might be like lifelong macroeconomic interventions, like things that change the growth rate of the economy, like writing a new constitution, putting in a new, whole new economic policy for the whole country, having a revolution. Their income effects might start to matter. Or things that affect one individual in some way that changes their whole life. So those types of things tend to show up in development economics. So sometimes in macro and development, income effects do matter. But for most of this course, which is not going to talk about either macro or development, none of these things are going to matter. And our life gets so much easier as a result of that. Consumer surplus becomes easy to calculate, and we can aggregate it across individuals really easily. Pareto efficiency becomes equivalent to maximizing people's willingness to pay. Because if we maximize everyone's income and there's no income effects, we can always just redistribute the wealth however we want. Equilibrium is just like individual maximization, because once individual demand functions are symmetric, if you add up a bunch of symmetric things, you get something that's symmetric. However, there are a couple of issues we'll consider where I think income effects might be relevant, though in fact we'll end up ignoring them anyways. So one of them is optimal taxation. So if you're thinking about reforming the whole tax system in a really dramatic way that might double tax rates, that could really have important income effects. Or setting up a constitution or a war or something like that, which we'll talk a little bit about stuff like that in this course. Okay, so that went on a little longer than I hoped, but why don't you guys take a 5-minute break and we'll come back and talk about applications of general equilibrium theory.